we have a curve, one above, one below, then we're going to use the y coordinate on top, subtract the y coordinate at the bottom, and then integrate, right? What happens when you have curve one is on the left, one is on the right? For example, like this one. So for example, like this one right here, okay? So one is on the left, one's on the right. So how can we find this region bounded by these two curves where y go from C to D? Now, the idea is very similar to the one that we have go through. So we're going to approximate them by Riemann sum. Okay, so, and then each rectangle, each approximating rectangle over here, the width over here will be delta y, so that will be dy. And the length over here will be the x coordinate on the right, subtract the x coordinate on the left. Okay. And the y here go from C to D. Okay. Notice that when you calculate the area between two curves right here, we use this y coordinate on top, subtract this y coordinate at the bottom, and then integrating this x here go from A to B. Okay. Now, what happens when you have this curve on the left and the curve on the right, and you try to find this region bounded by these two curves where y go from C to D? Well, the idea is similar. We also use Riemann sum, and the typical approximating rectangle will have this dimension to be the width to be delta y, and the length over here will be x coordinate on the right, subtract the x coordinate on the left. So this area over here will be equal to this integral of x coordinate on the right, subtract x coordinate on the left, and the y over here go from C to D. Example 5. Find the area enclosed by this line y equal to x minus 1 and the parabola y squared equal to 2x plus 6. First, we want to find the intersection point of these two curves by solving this system of two equations together. Notice that when we solve this, we can use the substitution method. So substitute x minus 1 into y, expand that, and combine I chain, factoring, and we get x equal to either 5 or -1. So the corresponding y will be 4 or -2. So the two intersection point here will be 5, 4 and -1, -2. Now those are the two intersection points. The 9 right here is y equal to x minus 1. It is this 9 right here with the y-intercept equal to -1 and the slope equal to +1. So this is y equal to x minus 1. Y squared equal to 2x plus 6. This is a parabola open to the right. And will be like this. Intersect this line right here at this point and this point. So it will be like that. So we know that this is on the left side of this line right here. We're trying to find the region here. So to find the region, we're going to use the formula. Use this formula over here. We need to find the x coordinate on the right side. So for each typical approximating rectangle, so what will be the x coordinate on the right? Now, on the right here, this is a straight line. We got y equal to x minus 1. So we can isolate the x over here. We got x equal to y plus 1. So x coordinate on the right will be y plus 1. This is the x coordinate on the right. Okay. So what about this parabola over here? This parabola is given this equation. So you can solve for x over here. After you solve for x, then we find that the x coordinate on the left will be equal to this. So use the formula. You integrate. So use the formula. This area between this curve and this line right here is given to be the integral of x coordinate on the right, subtract the x coordinate on the left, and the y here go from -2 to 4. Now, xr is y plus 1. XL is 1/2 y squared minus 3. After this, you're going to simplify this. So combination, we got this one right here. Now we just need to find antideuty of each term right here. Antideuty of y squared is y cubed over 3. Antideuty of y is y squared over 2. Antideuty of 4 is 4y. So we evaluate this y here from -2 to 4. So substituting here, we got 18. So 18 is this area between this curve and this line right here. Right? So that's the end of our lesson today. And I'll see you guys next time.